Okay, hello DE. So this is Mr. Lun, and I wanted to not just show a PDF of the work, but I would like to actually give you guys a explanation as I do things. So the problem with circuitry is not just that it's confusing, it's just that it's conceptually weird. However, with a little bit of practice, I genuinely think anyone can get pretty good at it. The math behind it isn't too bad. The worst you'll have to do is two variable systems of equations. We'll do one or two of those. If you go into computer engineering or electrical engineering, so in college, you will be doing nodal analysis with 3, 4, 5, 6, nodes, where there's how many nodes there are means directly how many unknown variables there are. That being said, for this class, you'll never see more than two. Mostly because solving a system of equations that has more than two unknown variables is extremely annoying, and I'd rather just not deal with it. And it wouldn't help you guys either. It'd be a lot of class time on how to solve a variable systems of equations of and it would be a waste of time. So that being said, this is a one variable equation. However, the setup is a really weird one. So what I would say is right here. So when you do nodal analysis, you want to identify the node. So the node, or you heard me call it a junction, is basically where a wire splits off. However, I think another good way to think of it is that it is like a single, it's all one single wire, all one single connection. R1, R2, and R3 are all connected by this middle area here. That is all one node, one junction. So in our case, most of you were able to identify that this right here is what is the node that we should be analyzing, and partly because the currents were drawn in the problem, making it pretty clear that we want to be looking at I1, I3, and I2. And so when you do nodal analysis, the end goal is that you get the voltage at that node. Which means if you put the negative terminal on a voltmeter on ground and put the positive terminal on the node, say when we built this on the breadboards, the voltage that we find will be the number you'd find there. You're just finding what the voltage at that node itself is. However, that being said, identifying that we just do not know what this voltage at that node is. So in order to solve using nodal analysis, all you really need is a few things. You need to understand KCL, and you need to understand Ohm's law. So now KCL is where a lot of people get confused and stuck on when they first start doing nodal analysis. So KCL, or Kirchhoff's current law, is honestly very straightforward. It's just weird until you get used to it. So Kirchhoff's current law states that the current going into a node is equal to the currents coming out. You can think of this as a pipe with water in it that splits off. The total amount of water is still the same before it splits off and afterwards. We're just saying that the current that goes into the node, or in our case, I2, is the same as the current that's coming out, or the sum of the currents coming out. Like I was saying, it's a conservation of energy. Current is the flow of electrons through components, meaning that there has to be the same amount of electrons flowing in total before and after a junction or a node. I'll go back and forth mostly because I don't know exactly what physics teachers might be using and all the like. So most of you got that I2 is equal to I1 plus I3. So the reason why is that I2 is entering the node and I1 and I3 are leaving it, meaning that I2 is equal to the currents coming out, which is I1 plus I3. So now that is the KCL done. Now Ohm's law, so Ohm's law is V equals I times R. The voltage across a component is equal to the current that's going through it multiplied by the resistance of the component. Luckily for us, in this circuit, everything is labeled 1, 2, and 3. So we can break down I2 as the voltage across R2 over the resistance of R2. And we can do that for all three. So these currents are the currents going through each individual resistor. So the current going through the resistor 1 is the voltage across resistor 1 over the resistance of resistor 1. The current through resistor 3 is the voltage across resistor 3 over the resistance of resistor 3. So we know the resistances, so we can just plug that in. R2 is 570. R1 is 220. So this is where the confusing aspect of voltage comes into play. The voltage across a component, whether it is a resistor, transistor, capacitor, whatever, the voltage across a component is saying the difference of voltage across that component. So right over here is another node. So a good rule of thumb is that any node connected to a negative terminal of a battery is considered ground. So ground meaning 0 volts. So this whole bottom node we can assume to be 0 volts. So if you look at resistor 2, the current is flowing upwards towards the node, or upwards towards V. So the voltage from here to here is 0 to V, meaning the voltage across resistor 2 is actually 0 minus V over 570, or not, let me rephrase that, I'm sorry. The voltage across resistor 2 is 0 minus V. The voltage across resistor 1, it starts here, ends here. The voltage on this side is just 9 volts because it's connected directly to a battery. And the voltage here is just V. It's connected to that node. So it starts at V and it ends at 9. The voltage across resistor 3 starts here, ends here. The voltage right here is V. Oh my god. The voltage right here is V because it's connected to this node. The voltage right here would be 9 because it's connected directly to the battery. So starts at V, ends at 9. So from here, most of you, if not all of you, hopefully can solve this for V, but that doesn't give you the final answer. So I can help walk through solving this for V really quickly. First thing I will do is 0 minus V is the same thing as saying negative V. I also have a 0 with all of these, so I can actually cancel them out. If you're not sure why, it's because I can multiply everything by 10, and that would effectively be the same, or not effectively, but is the same thing. 10 times this equation right here would just cancel out the 10 and the 0. And same thing over here. And then I would just multiply everything by just every denominator. So 57 times 22 times 33. 57 times 22 times 33 times 57 times 22 times 33. So the 57s here cancel out, 22s here cancel out, the 33s here cancel out, leaving us with negative, and I guess plug this in my calculator, 22 times 33, 726V is equal to, this is 57 times 33, 1881 V minus 9 plus 57 times 22. 1254 V minus 9. So a big reason why I canceled out the 0 over here is because I already could tell that these numbers can become big. So anything you can do to try to minimize that is just going to make your life a little easier. You can make your life easier all the time. The easier you make your problems, the easier you'll do. So one thing I can do here as well, both of these terms have V minus 9, meaning I can actually just factor this out. So V minus 9, and this would leave 1,881 plus 1,254. And let me not forget the equal sign. And I can just plug this into my calculator. So negative 726V is equal to 3135 V minus 9. And just one more time, plug in my calculator. Negative 726 V is equal to 28215 V, or oh my god, I mixed up my numbers. Sorry about that. I'm sorry. 3135 V minus 28215. I distributed this outwards. To solve for a variable, you got to get all your variables on the same side. So subtract 135V to both sides. Negative 3861 V is equal to negative 28,215. Solve for V, we just divide both sides by 3,861. And this gives us a voltage of 7.3 volts. The numbers get a little crazy, but in all honesty, the reason why this became so crazy was mostly because all the resistors that we can use in real life are a few hundred ohms. When we do more practice, we'll be able to use smaller numbers, meaning the math will be a little easier. I just wanted a circuit that you guys can make and analyze yourselves using the digital multimeters. So that being said, we found the voltage at this node. If so, right here, we can actually cross this out. It is 7.3 volts. If we took a DMM or digital multimeter, put the positive probe right here, and put the negative probe on ground or at the negative end of the battery, we'd get 7.3 volts. So, that being said, we don't know the currents. So, I2, or we have written here that each current, negative V over 570, I3, I1. We didn't explicitly write these equations, but I3 was the 330, V minus 9 over 330, V minus 9 over 220. But we implied it when we changed out these variables. So that being said, this is my first time teaching it to people who have not formally learned it. So there's gonna be times where I genuinely overlook or not think about your situation. So if that happens, just speak up. Tell me like, hey, we need to like talk about this more, do more examples, something. My perspective is still skewed. But according to Ohm's law, the voltage across a resistor divided by its resistance gives us the current. And we said the voltage across the resistor, or R2, was 0 minus V or negative V, meaning negative 7.3 over 570 negative 0.13 amps. We haven't talked too much about scientific notation. Well, not scientific, engineering notation. We will. But right now I would accept this answer. In a few weeks, you'd have to put your answer in engineering notation, or also known as... Oh, I actually wrote my thing wrong. It's 0.13 amps. So, engineering notation, we go back 3. So it's negative 1, negative 13. Going back 3 means milli. So negative 13 milliamps. (7.3 minus 9 over 330). Putting that in the calculator gives us negative 0.005 amps. Like I said, we'll talk about scientific notation, how to do it. It's honestly pretty quick. We'll probably spend a day or two literally just on how to do it. If you have the TI-89 like I do, the hack is literally that in the settings, you can turn on engineering notation and it'll give you perfect answers every time, and you just don't have to think about it. Oh my god. But I've also just been doing this for so long. Not 500. Jeez. Negative 5 milliamps. And then 7.3 minus 9 over 220 is equal to negative 0.008 amps. Equals negative 8 milliamps. So this is a good amount of math, and I'm honestly still dying a little bit here. So sorry about that. We will do a lot more practice on this. The curriculum actually does call for a review for up to a month. So if you feel lost, don't be afraid. The only thing I want to talk about right now is mostly why our answers are negative. So if you get a negative answer for current, don't be afraid. It just means that it's actually moving in the opposite direction. So I can actually just do a bright color here. Our current here is actually going into this. So I1 was 8 milliamps. All three of them are negative. This one was 13. Right. No, I did that wrong. That one was 5. That's all that means. A negative answer just means that it's in the opposite direction. Like, there's honestly nothing to be worried about. And then if you want to make sure that your answers are right, all you have to do, so I2 equals I1 plus I3. I1, or let's see, so I2 is negative 13 milliamps equals I1 was negative 8 milliamps plus negative 5 milliamps. All these negative signs we can cancel out. Does 8 plus 5 equal 13? Yes, it does. It fits KCL. So, one thing, if you can, I would like you just to look at the breadboard activity we did and see how close our numbers were here, because we calculated our current with the voltage we measured across the resistors. So so just curiosity, if you also want to check and see how close we were. So have a great night. We'll see you tomorrow. DE.